Okay. So I'm Solene Mirliaz, as said, and I will present a Flow-Insensitive-Complete program representation for static analysis. So there is currently a trade-off in static analysis between precision and speed. And here precision is an informal concept of how many false alarms you are raising, because if you raise a few false alarms, there is less manual check, so you tend to prefer precise analysis. Now, if you want to design an analysis, you have the choice between a flow-sensitive or a flow-insensitive analysis. A flow-sensitive analysis will track one invariant per program point, so you are usually more precise, but at a cost because you need to maintain all these invariants. If you are more concerned about the cost, you will maybe prefer a flow-insensitive scheme where you have only one invariant for the whole program, but you may lose some precision. Now let's look in detail these two kinds of static analysis on an example. So here I've got an example with a program with two variables, I and j, which are incremented in a loop. I is used as a condition to leave the loop, and I want to check at the end of the loop iteration that j is indeed between 10 and 20. If I do a flow-sensitive static analysis, I will try to have one invariant per program point. And a way to do that, to see the semantics of this program, is to, for each program point, I will look at the predecessors, and I will apply on its invariant the block between the predecessor and my current program point. And so you can see how for the initial state, the entry point, I consider I and j to have any value, and how I apply all the instruction per block. If I want to formally define this set of equation, I say that my local invariant is a function from program point to a set of states.
So, sorry, we have an issue with the slides that are not displayed correctly.
Oh yeah.
Only they are on our side, not on the projector. Only they are fine. So give us one moment, sorry.
Okay.
Perhaps can you restart the speech?
Restart the speech? Okay.
The speech area.
So, yeah, maybe just with this slide.
Restart the screen share, not the speech, if possible. Thank you.
Yeah, okay. Yeah, there is still a problem. Okay.
It was good. Yeah.
Is this better? Okay. Okay. So, yeah, I was saying that my local invariant is a function from program point to a set of state, such that for the entry point, I will consider my initial state as 0, with I and j having any value. And for the other program point, I will look at the predecessors and apply the block. And if I've got several predecessors, I make a join. Now, if I want to make a flow-insensitive analysis, I will represent all this information, all these different invariants, into a single one, and a way to do that is to merge all this equation with join. The issue is that when I want to try to find the fixed point of this equation, everything will be merged in a single state where I can say that I and j can have any value, which is sound but not precise. Formally, we will say that our global invariant is a set of states, and which must contain the initial state and which must be stable by the application of any any block and any sequence of block. Now, the issue is that you lose a lot of precision, when you do this merge. And so actually, when you want to do a flow-insensitive analysis, you rename your variable so that you can make a difference between your initial variable and the one in the loop and the one after the loop. And one program representation that helps to do this flow-insensitive analysis is the SSA form, static single assignment, where you have the property that a variable will be assigned only once in your program. So every time you find a new assignment, you rename your variable. And here on the small example, you can see how I've introduced a version x0, x1, and x2 to respect this property. However, if I've introduced two different versions of a variable in two different branches, when I want to use x afterward, I need to somehow join this information, these two versions. And that's where we need the phi function at the joining point, which has the semantic to take x1 and assign it to x3 only if we came from the left branch, and x2 to x3 if we came from the right branch. With this renaming of the variable, if I perform a flow-insensitive analysis on this right example, I will be able to say that x4 is always negative. However, it's not always the case that we can keep the same precision than the flow-sensitive analysis. And that's why more program representation were introduced. For instance, the static single information form, SSI, which have a stronger property. A variable will have a constant information for all its live range, meaning all the program points between its definition and its use. So of course, you must respect the same properties as SSA, because if you do an assignment, you change the information on your variable. But you need also to introduce a new version when you have a condition, because when you pass a condition, you gain new information on your variable. So if I go back to my small example in SSA, I need to introduce two new versions for x0, one for the left branch and one for the right branch because of the condition. And these versions are assigned by a sigma function, which has the semantic to assign x0 to x5 only if we are taking the left branch. So during the life of x5, we are guaranteed that it will always be negative, and similarly, x6 will always be positive. So where we gain, where we have a benefit of using SSI compared to SSA is, for example, if in my right branch, instead of having the condition and the assignment of x2 in the same block, some other thing happen in between. Well, if I perform a flow-insensitive analysis on my SSA version, I will not be able to predict the sign of x2 because x0 can have any sign in this program. However, because I've done some splitting with SSI, I know that x6 is always positive, so x2 and x5 are always negative. So here I've got more precise analysis thanks to the splitting. Now, SSI is still not enough, as we will see on the first example. I've put here my example in SSI form, and so you see how I've introduced, for example, new version for I and j I1 and J1 at the joining point, how I've split I1 into two versions because it is used in a condition. So I now have I2 and I4. But now if I do a flow-insensitive analysis on this program, I still need my invariant to be sound when I apply the initial block with the phi function. And so I will have a state where J0 is equal to 0 and J1 is equal to 0 in my global invariant. But I need also to be stable by the assertion where I use J1. And here you can see how the assertion will be violated if I do a flow-insensitive analysis, despite being in SSI form. So this representation is still not enough because here I'm trying to have a relational property between I and J. And SSI is made for non-relational invariant because I'm only tracking the information for one variable instead of a set of variables. So we need more than SSI. And we could even argue that some of the copy are not strictly necessary because here, for instance, I4 is not necessary to prove the assertion. So maybe we need a finer criterion to insert copy. And that's the goal of the paper, to find a good criterion to insert copy for variable, to keep the same precision in the flow-sensitive analysis and the flow-insensitive one. If SSI is not enough, we could argue that doing a full SSI where we insert copy at all branching points for all the variables could be enough. But the problem if you do that is that you introduce so many variables that you completely undermine the goal of flow-insensitive analysis. You will have a big invariant to manage instead of several small ones. So we need to do better than that and to have a fine criterion. To obtain this criterion, we first need to formally define what we call precision. And we will do so using only the collecting semantics and no abstract domain so that we don't lose precision because of this abstract domain. And when we try to prove that we keep the same precision in the flow-sensitive and flow-insensitive analysis, in the proof, we will find where we need new copy. And that's how we define the properties that must be respected to have a flow-insensitive-complete program. And finally, with this criterion, we try to design a transformation from SSA to FIG form, which respects these properties. So first, let us talk about the precision, what we mean by that between a flow-sensitive and a flow-insensitive analysis. As the goal of the analysis is to prove assertions, we will measure the precision with respect to the assertion violated by both analyses. And so I define the fail state omega to be the result of the application of an assertion on a state that violates the assertion. So on the previous example, here I've got a fail state omega when I apply this sequence of block. And what I want is that for my central theorem, if my program respects some FIG properties, then I will find fail state in my flow-sensitive analysis if and only if I also find fail state in my flow-insensitive analysis. Now, at this point, we really are talking only about collecting semantics and no abstraction is involved. To prove this equivalence of precision, we have two implications to prove. One is quite easy. If I've got an assertion violation in the flow-sensitive analysis, it means that I've got a sequence of block which raises this violation. And I will find the same sequence of block in my global invariant because I do not enforce any order. However, because I do not enforce any order, I will consider sequence of block in my global invariant, which are not feasible one. And so I need some property on the program to guarantee that even though I do not respect any order, I will still have states that are coherent, equivalent to states in the flow-sensitive analysis. And if I can prove this equivalence, I have my central theorem. But I need properties on the program. And these properties are what define flow-insensitive-complete form. And in the next part, I will present how to obtain programs that respect this property, and finally show the result of some preliminary experiments to see if the number of variables inserted remains reasonable to do a flow-insensitive analysis. So we've identified two properties to respect. The first one is that if variables are used together in a block, then they must be defined also together in a block to remain coherent between them. And the second property is that from the definition point to the use block, for any state, we must find a path that will not block the state and that will not change the value of the variable. So if I go back on my example, enforcing these two properties means I need to insert a two copy. So the first one here is for J1, because J1 and X0 were both used in the two bottom block. So if they are used together, they must be defined together, which was not the case. X0 was defined here alone. So I need to introduce a new copy for J and J5, so that X0 and J5 are now defined in the same block and respect the property 1. Another copy I need to introduce is here also for J1, because it was used in the assertion, and it was defined before the program point L1 by the phi function. So there are some states that must go through the condition I1 greater than 10 before reaching the assertion. And since some state can be blocked by this condition, we did not respect the property 2 with the previous setting. So we need to insert a new copy here for J1. Now, the issue with property 2, property 1 can be checked statically, but property 2 is a semantic property on the program, because we are talking about paths that exist for some states. So instead of this condition, we found sufficient conditions that the program must respect for it to respect property 2. The first two that we admit are the termination and the well-structuredness of our program. And the last one is the existence of a constant path from the definition block to the use block. And a constant path is a path in the dominance tree, which will contain no redefinition, no assertion, and no condition. So we can check that statically. And in fact, this gives us the algorithm to insert copy to respect property 2 and to go from an SSI program to a FIC one. Back on the example, how did I determine that I need this copy? Well, I did a bottom-up traversal of the dominance tree to check that I had constant paths. So here is the dominance tree. If I start with the assertion block, I see that I use J1. So I will go up the dominance tree to find its definition. And by doing so, I will find the condition which violates property 2. So I need to insert a copy. Similarly, for X0 and J1, I need to go up the definition tree to find definition of both variables. And I will find a redefinition of X0 without the definition of J1. So again, I need a copy. So you can also have an idea of the complexity of this program, of this transformation, with this example, because I need to do this check for all the variables for each block. And in the worst case, I need to go up the whole dominance tree. So if it has a height of h, then the complexity of this algorithm is h times the number of blocks times the number of our original program, which is in SSI form. So it's not as good as the transformation to SSA, which is mostly linear. But if this form does not introduce too much variable and allow flow-insensitive analysis to be performed quickly, then it's a price we are ready to pay. So about this price, we did some early experiments to see how many variables were introduced in practice. So we took some real Java programs from different libraries, for instance, for static analysis. And for each function, we apply the transformation and we count the number of variables introduced. Now, what we want to compare is not just the number of variables, it's actually the space needed by each kind of analysis. So first, we will consider the space needed by a classical textbook flow-sensitive analysis performed on the SSI form, where the size of all the invariant is the size of one invariant times the number of program points. So here, the size of the invariant, we choose to square the number of variables, because if you are looking at relational invariant, quite often you will have an invariant which is a matrix or which has a size equivalent to the variable squared. Now, this is really a textbook analysis, and in practice, for example, in the tool Pagay, we do not track for every program points because we know it's inefficient. So instead, we only keep the invariant at joining points because that's where you want to build your fixed point. So in a second time, we compared the space with the one of a more economical flow-sensitive analysis. And these two flow-sensitive analyses are compared to a flow-insensitive one, but this time performed on the FIC form. And since it's a flow-insensitive analysis, we only have one invariant, so we just square the number of variables in our FIC program. So these are the results for the flow-sensitive analysis, classical one, compared to the flow-insensitive one. Each dot is a function in our benchmark. On the vertical axis, you have the size needed for the flow-sensitive analysis. And on the horizontal one, you have the one needed for the flow-insensitive analysis. The line here is the identity function, which serves as a reference. And you can see how, compared to a textbook analysis, where in the vast majority of the cases, we need a smaller size, a smaller space than the flow-sensitive analysis, which is quite encouraging for the performances. Now, if we look at the more economical flow-sensitive analysis, here we cannot have a clear answer. In some cases, we are better, and in some cases, we are worse. So it's still encouraging because it means that in some cases, the flow-insensitive analysis may perform better by using less space. Now, this is only a preliminary result, and we still need to implement the different static analysis to compare the performances with the flow-sensitive scheme and the flow-insensitive one. So to sum up, we defined a notion of precision and a condition to have an equivalent precision between the flow-sensitive and the flow-insensitive analysis. We designed the transformation which will ensure that this property is respected by a program. And we made some preliminary experiments to check that it was feasible to do a flow-insensitive analysis with this FIC form. And we see that the preliminary results are quite encouraging. Now further works include to test it on a real analysis to see the performances. Thank you for your attention, and if you have any question.
Thank you very much. Any questions? Let me maybe start. Can you perhaps comment on the cases where the naive SSH transformation was in values of smaller size? You do a more detailed analysis of these cases?
So, yeah, sorry, I didn't get the end of the question. You were asking for the naive analysis, naive static analysis?
In your comparison, there were cases where the naive SSA transformation gave better results.
Yeah, okay. So in this small example. Yeah, so it can happen if the program is like one block, because in that case, you don't introduce, no, sorry, if the block decomposition is not optimal, because then our flow-insensitive analysis, our transformation, sorry, will introduce many copies that are not necessary for the analysis. Sorry, it wasn't really clear. So yeah, there are some corner cases. I did not inspect all of them. If my memory is correct, some of them were like huge switch case. So like for SSI, it would also be a problem because you introduce copy for all the variable implying the condition. And here it's the same problem. We will need to introduce copy everywhere because all the paths contains condition. But I'm not so sure about this benchmark. I think it's the case for this one.
Thank you. There's one more question from the remote audience. Victor Kunchak asks, how do you deal with values stored and read from arrays and the heap?
So we do not deal, we do not deal with this for the moment. We are interested in numerical analysis so far. So this is not of our concern in the precision evaluation. We consider a language where we don't have arrays on heap for the moment.
Any more questions?
Hi. In your for your transformation from insensitive to you have a relaxation from some semantic condition, syntactic condition. Does that mean that before there could be a finer grain transformation?
I did not get the end. So you were asking about some modification of property?
Right.
Get property too?
Right. Does that mean there is that there is maybe a finer grained algorithm that you could perform to have like fewer extra variables here?
Not that I think of, because we have an algorithm here that can transfer the program statically, which is kind of the point. While the property 2 here, it would be really hard to ensure that we can find a path for any state. And in the proof, you can see that if, for example, I encounter in my path redefinition, but which do not really change the value of my variable, then I will still be able to prove my theorem. But it's hard to tell that an assignment will not change the value in your state. So it was a compromise between feasibility and precision here on the number of variables introduced. And I don't see a simple way to reduce the number of variables we introduce. Now, what I did not talk about is that here, since I'm targeting some assertion, a first step, which can be done for any analysis actually, is to do some slicing to clean your code from any variable that is not necessary to prove your assertion.
So let's thank Solene again.